So next we're going to talk about the debugger. Now, y'all didn't use a did y'all use a debugger in procedural? Any? Like GDB, DDD? Well, you did Visual Studio, right? So when your program failed, did it like bring up a console and tell you what line was the problem?
Yeah.
Okay.
A certain line has an error.
Oh, okay. So they integrated the debugger inside of an IDE. Well, that was certainly nice of them. So hopefully you can tell from the command line, you no longer have that. So let's go ahead and I'm going to go and create a broken.cpp. Always a great name. Let's see. Oh, I need to get my tabbing done right, huh? For it. All right, let's see if that breaks. It didn't. Oh, that's because I didn't actually do anything. Huh. Let's get rid of some. Let's do that. Segmentation fault. Perfect. All right. Is this the first time you've seen this? Yes, for a lot of you. All right, segmentation fault. You're going to get this a lot. What that means is you accessed a piece of memory that you did not have permission to. You're out of your program's segment, and there was a fault that was thrown. And so it's a segmentation fault because you're out of your segment or within the bounds of your program. By the way, can anyone see where that happened? I'll break this out because I made it all one line. So how many integers have I created on the stack? Oh yeah, we'll have to do memory. Hopefully we'll do memory next time.
Two.
And how many nums? So that integer nums is an array of how many elements? 1024, right. So what's the issue with my for loop? It's too big. You're on the right track. You're on the right track. A little more precise. You're on the right. Right. How many integers am I trying to set here? Over 1 million, yet my buffer is only 1024. So I'm basically trying to access memory, which is segfault. Well, let's go ahead and say, for some reason, you didn't know what was going on. You do G++ and you want to run the debugger, so you do a.out. It's going to come up with this tool, or this little command prompt over here. You type in run. It'll start the program, and it says received a seg fault in main. Well, unfortunately, that was not too useful, because it just says it was a seg fault, which you already knew, so thanks, guys. You do Control D in order to get away from it, to quit. But if you want the debugger to be helpful, you need to pass in the -G flag, which stands for add debugging or GNU debugging symbols to your binary. And you can still run broken, a.out, segfault. Now if you do gdb a.out, you do run. It tells you right there, line 7 of main. The error is right here. So it's on num. And you can print I. And I is currently the value 1764. Ooh. So here's a very important question. 1764. So it's saying when I is 1764, it caused a seg fault. But wait a minute, how many values were inside of num?
Less than that.
Yes. Does anyone see an issue here? Or do you think the tool is wrong?
It's out of bounds.
It's still out of bounds, but doesn't that mean that it wrote, was it 5 over 700 integers before it had a seg fault? Because it should have seg faulted at what? 1024, right? But it didn't. This is where a lot of your security errors come from. When you write a program in a language like C++, it doesn't do the bounds checking. The operating system or the hardware has to do it. And it may not catch it until you've gone way, way out of bounds. Therefore, you can actually write outside of where you're supposed to a good portion of memory before anyone will catch it inside of C++, and you will not notice it. This is why you have to be careful, and also why a lot of times when you see, oh, the new security vulnerability, either buffer overflow, another popular one is use after free, this is what's going on. You still could legally access the memory, you just weren't supposed to, but you did it anyways. Of course, what this implies, we'll go ahead and quit, is if I open up broken.cpp and I change this to, we'll just say 1200, this should still segfault because you're going beyond the length of nums. But if I compile it, oh, it did segfault, yes! So we'll go ahead and shorten that a little more. We'll go to 30. Hey, it ran. Should have given an error? Yes, because, yeah, you're going to go beyond the bounds. So keep this in mind, because there was no segfault, and GDB didn't tell you what's going on. So the question is, how can we automate fixing or finding these errors? There is a tool for that. It's called valgrind. You run valgrind on a.out. It's going to run it. Oh, it didn't find any errors. Ooh, that was terrible. Well, it looks like valgrind has failed us as well. So in this situation, you just have to be extra careful. Probably what's going on, I know what's going on. Did y'all do the heap in procedural? No? Okay. Well, but y'all have done new, excuse me, in OOP, right? Okay. Well, it's going to look a little differently because I have to do an int pointer. I haven't told you what a pointer is yet. We'll have to get to that. We don't have time for that today, so I'll make sure I do that tomorrow or next class. Sorry. By the way, do we have Monday off or no? I don't think we do.
I don't think so.
No. Yeah, we have school on Monday. Yeah, because we don't labor here, we work.
Well, we don't have to have class.
No, we're having class. Oh yeah, no, you need all the time you can get, okay? Nothing's worse than at the end of this class having to do like 2 of them in one session. It'd be awful. All right, so G++ broken.cpp, a.out, doesn't segfault, valgrind a.out, and oh boy, there they are. Let me go ahead and pipe that to out, and I meant to use a 2. There we go. Then the output of valgrind, invalid write of size 4, 0 bytes after block of size 4096 has been allocated. Ooh, why does this say 4096 even though our array is 1024? So we have 1024 right here, but valgrind reported that we're using 4096 bytes, but the array length is 1024. What's going on?
in memory is 4 bytes.
What's 4 bytes in memory?
Yeah.
No, what is?
Well,
An integer, right.
Yeah.
So in C, an integer is 4 bytes. So you have each cell is 4 bytes. You have 1024. 4 times 1024, 4096. So keep that in mind. So it's reporting the bytes consumed. All right. Let me go ahead and jump back to the slides to make sure I've gone through everything. We did Q quits the debugger. You can run it, so we went ahead and did that. You can set breakpoints, but we're not going to. You can list, wow, the lines. I've showed you the ones that are actually important. Okay, we don't need to do that. We're not doing that. Print I, that's the one that was important. So the one I showed you is when you segfaulted, you can print I and it'll tell you the value of I. At that point, 1,764 or something like that. At other times you can print what the value is, and that should give you an idea of what was causing the error. You can ask me where it is, and the other last one I really want to show you. Oh, this one doesn't. Let me go ahead and get the error to come pop back out. Boom, boom. Perfect. So, oh, did we not do the flags? No, I didn't. -G for the flags, gdb a.out, run it. All right, so I did print I. This time it was 33,000. Wow, got a lot of room that time. Oh boy. And then the other one I want to show you is info stack, and right here it wasn't too helpful because it just tells you you're on line 7 of broken.cpp. But when you're calling function inside a function, find inside a function, you do info stack, and it'll give you the entire stack trace. Just kind of, just like in Java. You know, Java gave you the stack trace of where you were. This will do the same thing, info stack. Okay. I put it up here because every once in a while, when you do segfault, you'll get a core dump, and it will produce a core file. What's nice about a core file is you can open it with GDB and then inspect the entire program. They started disabling this by default, but if your error is really, really, really bad, you can still get a core dump. In which case, I want to know what you did because I haven't seen one in a long time, but I know it can be done. In which case, you run GDB on the core, and then it will actually bring it up, and you can inspect what's going on. Oh, someone asked a question? All right. Okay. Let's see. So kill, all right. Last off, you can use DDD, which is the GUI wrapper around GDB. This will allow you to open up the source code, put in breakpoints using a GUI, and then you can hit next instead and watch your different variables and whatnot. If you're really into using that, please feel free to go ahead. Okay. Oh, we're gonna finish early. Yes. Yeah. Okay. I'm not going to go through the full computer architecture about how everything is laid out, but it's important to take a step back and to see the big picture of what's going on with your program, because certain errors that pop up are going to be really confusing unless you understand high level what's happening on your machine. So at the heart of your system, or the operating system, you have the kernel, which is what's managing all your different devices, and you read and write, or you run different system calls in order to interact with the kernel. So keep in mind that when you're running a program, it's running on top of the kernel, which is provided by the operating system. So you have your Windows kernel, your Linux kernel, your Mac kernel, so forth and so on. The kernel is the interface from your program to the hardware. Okay? Something more like, let's see, there we go. So you have your user space. This is the program that you're using. You use a library, which is maybe the C++ STL, or printf, whatever you call cout, you're using a library. but that library still exists in user space. The library is what calls the kernel in order to interface with your hardware to display different commands. This is going to come up every once in a while with either permissions or other types of errors that pop up. But just keep this in the back of your mind. So valgrind, actually we started showing that a little. Memory for memory debugging, memory leak detection, and memory profiling. So when we did valgrind beforehand on broken, valgrind, a.out, perfect. It spelled out a bunch of errors, and then down here it said that you definitely lost this amount of memory. All right, what is going on? So in Java you did new, but what did Java have that was nice? Or actually, I'm sorry, but Java had a garbage collector, and so it automatically cleaned up all the memory for you, so you didn't have to free it. C++ does not do that for you. So you have to do it manually. And what valgrind's telling you right here is that you left open 4,096 bytes of the system without closing it. So how do we fix that? Well, I'm going to go over, take broken and copy it to fix so you can at least see what the old version was. And we're going to go ahead and change this to 1024. I'm going to make this equals just to do something at the end. So this is how it works. For every new, make sure there's a delete. So when you create something with new, make sure you delete it afterwards. So down here, we're going to do delete. And since this was an array, we're going to do an array delete on nums. All right, and that'll tell G++ to go ahead and clean this all up for us. So let's go ahead and G++ -G fix. We'll go ahead and put it out to fix. And then we'll run it. And then we'll valgrind it. All right, in use on exit, 0 bytes and 0 blocks. That means that you freed everything you created, and then it just tells you that you had 2 allocations on the heap and you had 2 frees as well. And this had the number of bytes you allocated. That's all fine. It's just reporting how much memory your program took up. Depending on what your program does, how much it takes up, it just depends. That's okay. It's the use on exit that is what's going to cause an error, and it's important to take that into account because all your labs, once we start using memory management, if you don't clean up your memory, it's minus 20%, or not minus 10%, sorry. Minus 10% from your lab. So please run valgrind. Otherwise, you'll get some errors. But there is also another issue up here. Invalid write of size 4. So, address, whatever this is, actually it says in main, line 7, address is 0 bytes after a block of 496. So what this is saying is you allocated 4,096 bytes of memory, and then you wrote to the block that's right after it. 0 bytes after. So the block right after it, you wrote there. You shouldn't be writing there. C++ just, it ended up being okay in this situation, so you didn't segfault. But you're out of bounds here. Let's go see if we can find that. So it said line 7. So here's line 7. So what's the issue?
Can you repeat the question?
So, valgrind reported that on line 7, we have a write of 0 bytes after a block of 4,096. So you allocated 4,096 bytes, and then you wrote right after it, which you weren't supposed to do, which means you're writing outside the bounds. It ended up being okay because it's C++, but here's line 7. What is the error in our program? Yes?
Do you need to delete before you can write again? Instead of deleting afterwards?
No. If you delete it and then you try and use the memory, that's an error because that's a use after free. Because once you delete it, someone else may allocate it, and now you're writing over someone else's memory, which you shouldn't be doing. But you know, C++ might let you do that because it's like that.
Is it because of the less than equal to?
Yeah, why is that a problem?
Because you're including the 1024 making it.
And remember it in C, C++, what's that?
Is it one too many? Like
Yes,
you
it's
move
one
it?
too many. It's an off by one error. It's very easy to make an off by one error, was the point. Remember, arrays start at 0 in C++. So if you go up to 1024, you are outside the bounds of array of 1024. So we need to not have that equals. Now if we recompile it, valgrind fix. And when you see this from valgrind, you're probably okay. There's some good confidence what you're doing is correct. Obviously, you still could be messing things up, but there's a good chance what you're doing is correct. There are no errors, and there's a heap summary. Everything you allocated was free. It says no leaks possible. We're good to go. Okay. All right, so that's what it looks like. Oh yes, this number. This number over here, it's going to change every time you run it. It's the process ID. When you run a program on your machine, it allocates a process ID that's associated with that instance of the program. For this class, there's no need, but just know that for like operating systems, if you need to kill the process or do something with the process, you need to get its ID. So it's just telling you what the ID is. But for this class, it's not needed. So in this example here, hey look, new ints. Down here it said you definitely lost it. So in other words, I ran this program and then said that I definitely lost 4,096 bytes with this program up here. What's the problem with this program?
Didn't bring the data.
Yes, right. I'm not trying to be tricky, just trying to bring it home. Right, so we didn't free it. Definitely lost. Now, let me help you with what these mean. Definitely lost means not only have we lost the memory, you still have a pointer to it. So it's definitely, you definitely lost this even though you should have. Indirectly lost means there was a lot of nesting to it and at some point you lost the pointer, so it might take a while to figure out where it is. Possibly lost. If you come up with that, I'd like to see what piece of code you're running. Because I've done it before, but it's just certain times valgrind just can't decide if you actually lost the memory or not. Still reachable means that you, right now we're only allocating one array, but if you allocate an array with subarrays, but you don't delete every single subarray, then some of it is still reachable. So don't want to do that either. All right, so that's the correct version where we delete it. This is the one we just went through class. All right. The error, of course, was that we're using less than or equals. Don't forget to compile with debug flags. When you're using valgrind, it will actually give you all the information. If you run valgrind and it doesn't tell you what's going on, add -G. That way you'll see what's happening. Okay. Valgrind is a very, very useful tool. In some regards, it can replace GDB for you because it will actually tell you where your memory problems are. It does provide memory profiling and other uses, but that's beyond the scope of this class. Please use it. Please use it a lot, especially right before you submit your program to make sure you are freeing your memory. All right, here's a good question. Java has memory debugging built in, but C++ doesn't. Why did they choose to do it this way? First off, C++ could have done it, but they chose not to.
They want to be different.
They want to be different. Now, why would they want to be different here? Or are they just a little kid that wants to be different? Well, the only problem with, I see where you're going. First, no, but second, C++ is definitely older than Java. Java is the one that wants to be different. No. I liked it. I like that answer. Any other ideas? So if Java is going to take care of memory debugging, let's jump back to this picture. How big is the library? Ooh. So the library for Java going to be bigger or smaller by handling memory management? Bigger. All right. Is that a good thing? A bad thing? Both? So yeah, it depends. It depends. When would you want to have it? Or actually, when would you want to have it, or when would you not want to have garbage collection built into your language? I put memory debugging, but I meant memory freeing and deleting as well. Because Java automatically frees it for you, but C++ doesn't. Why was this decided? Why did they do it this way?
It's more efficient, so it doesn't have to keep like constantly checking.
So yeah, there are certain situations where it'll be more efficient. That's a great one, to not have the garbage collector run through your entire program. Because if you do run your program such that you free the memory correctly, then C++ will be faster. That's correct. But what's the cost of that? Not from a performance standpoint, but from a programming standpoint,
Longer.
it's going to take a lot longer, right, to code it correctly. All right, we also need to think of domains. If you're running a large web server with a huge machine, having the automatic memory management is probably not a big deal because you're already running a huge machine to take care of that. What if it's the computer inside your car? You're on a tiny microcontroller.
Space is important.
Yes, space is important. You don't have a giant machine to run everything. You also don't have the power. Well, I mean, you could put a bigger alternator, but then that would increase the cost of the car. People don't want to pay more for a car than they have to. They're already expensive. So, in that situation, you may want to run C++, which will have a smaller library, a smaller footprint, which means you can have a tiny microcontroller. You can also have faster response time in this situation. And so C++ is going to be or actually they use C, they don't even use C++, will be a better choice in that situation. And then there's a whole slew of everything in between. And we could sit there and debate different, different tools for different situations, depending on what you need. Let's see, what would be another good one? Ooh, how about if you're let's do medical, because this is always a great one. You have a machine that's trying to keep someone alive, maybe breathes for them while they're inside a hospital. These are tough questions, but that's why I'm asking them.
If that crashes, they're dead. It's like
Right.
a pacemaker, if that crashes.
You're basically dead, yeah. So which would you probably want to choose?
C++, because you're clearing it yourself.
Your semi clearance. Well, hold on. If you don't want it to crash, which of the two languages are going to be more crash resistant? Java will be, because Java's doing the automatic memory management and the exceptions, right? I think you
But
just.
with the pacemaker, it's small, you want
But with the pacemaker, yeah. So there were two different things going on. I was saying a large machine in the hospital, probably Java, because you have plenty of power. But a pacemaker, you need that power. It's mobile. You don't want the battery to go out, right? So you probably want to use a different language for keeping it small, even though you're going to have to deal with other issues that may come up. The most important thing about this discussion right here is there one solution that rules them all? No. Make sure that is very clear. What is the best one? It depends on the situation. All right. So next we're going to do a GNU plot. We've talked a little bit about makefiles and how to debug C++ programs. Next class, excuse me. We're going to use GNU plot in order to generate simple files or simple graphs to compare the performance of different programs. This is very important because as we move down the line to different data structures, each data structure is going to have different performance characteristics. And we're going to do both a theoretical analysis, so we can think of it from mathematically which one should be faster. And then GNU plot, as well as doing some timing information, will actually get empirical numbers, aka we're going to run it and find out which one is faster. And GNU plot's just going to plot it. It's just a plotting tool. You know, in Excel, plot this data, same thing, except for this class, it's going to plug in a lot nicer than Excel will. And hopefully I'll get to presenting perf, which is a tool that will show what part of your program is taking forever to run. Any questions about today before I go to the lab? Because I think there's a couple more topics on makefiles I need to go through. Nothing? Great.